We want to look at this question related to permutation with restriction, where we want to find the number of possible arrangements or permutations subject to some sort of restriction given to us. We're told in how many ways can six people sit in a line at a cinema if one of the six people, Andrea, must sit next to Scott. So we want to find the total number of permutations or arrangements subject to this restriction that one of the person, Andrea, has to sit to next to a specific person, Scott. So Andrea and Scott have to sit next to each other, right? So let's just lump them together in a box, right? They have to always sit together. The remaining four people don't have this condition, so it's one, two, three, four. Total, we have now five blocks, right? There are five factorial ways we can arrange these five blocks. Andrea and Scott always have to go together, so we've lumped them together in one block. So we have one, two, three, four, five. So the total number of ways we can arrange this is five factorial ways times 2 factorial, right? Where does the 2 factorial come from? Because we can arrange Andrea and Scott in 2 factorial ways. It could be Andrea Scott, or it could be also Scott Andrea, right? So basically, the answer to this is 5 factorial into 2 factorial. Why? Because the total 5 factorial ways, and you can arrange these. You can think about 5 slots. And then you can arrange Andrea and Scott in 2 factorial ways. And the reason we can multiply them is because of the basic counting principle, right? Because of basic counting principle, the reason we can multiply, because in 5 factorial ways you can arrange these 5 slots, and in 2 factorial ways you can arrange Andrea and Scott. So the total number of ways you can do both of them together is 5 factorial into 2 factorial, right? So this is how we would do this, because Andrea has to sit next to Scott, so we just lump them together, and now they have to move together, right? So you have total 5 slots, 1, 2, 3, 4, 5. One of Andrea and Scott, and the remaining four people. So this can be arranged in 5 factorial ways, and then you can arrange Andrea and Scott in 2 factorial ways, right? So total number of ways you can see them as 5 factorial into 2 factorial. Now let's look at the second part. And 5 factorial into 2 factorial, this is just 240. Right, now let's look at the next part. Andrea refuses to sit next to Scott. So now you want to find the number of arrangements or permutations given this restriction or condition. So there are two methods that we can actually do this. Let's apply method one first. Method one is number of ways without restrictions, right? Number of possible arrangements of these six individuals without any restriction. So without restrictions. Now, if I arrange them without any restrictions, there's six people, we can arrange them in six factorial ways, right? So there's six people, you can arrange them in six factorial ways without any restrictions, 720. So now number of ways if Andrea and Scott sit next to each other. Scott sit next to each other, and this we found in part A as 240. Right, these are the number of ways if we were to sit next to each other. This was given in part A. So number of ways if Andrea and Scott refuse to sit next to each other would just be the total number of ways, right, without any restriction, minus the number of ways Andrea and Scott sit next to each other. Right, so this would be 720 minus 240 is 480. So this is one way to do part B, where you find the total number of arrangements without any restrictions, and then from this you subtract the number of arrangements if they are to sit next to each other, which we found in part A. And the difference is going to be the number of ways if they refuse to sit next to each other. What is the second method to do this? So this was method one. Now let's do part B using a different method, method two. Now, method two is that we know okay, Andrea and Scott don't want to sit next to each other, right? So we have four people. They don't have an issue. They can sit over here, right? In these four slots, these four people can sit. Now, what we can do is Andrea and Scott can occupy these spaces between the four people, right? So we have these spaces. Now we have these four individuals that are seated in these four slots. Andrea and Scott, they can sit in the spaces between these four individuals so that they don't sit next to each other, right? So these are the spaces, because if they fill these spaces in between the four individuals, then they won't sit next to each other. Because if Andrea sits here and Scott sits here, or Andrea sits here, Scott sits here, here, so basically they will never be sitting together, right? They'll be filling up any space between the four individuals, right? spaces where Andrea and Scott can sit. And Scott can sit, right? So what you're saying is the four individuals can sit anywhere over here, right? And Andrea and Scott can take up spaces between these four individuals, right? Then they won't be sitting next to each other. So what are the number of possible arrangements if Andrea and Scott refuse to sit next to each other? Like we said, it's this. The number of ways you can arrange these four individuals is 4 factorial, right? So the number of ways you can arrange these four individuals in these four slots is 4 factorial, right? And then for Andrea and Scott, you can choose any two slots out of these five, right? Your total one, two, three, four, five. Out of these five, you can choose any two slots, one for Andrea, one for Scott, right? And then Andrea and Scott can be arranged in 2 factorial ways, right? So this is essentially 5p2, right? This is essentially that you choose any two slots out of the five slots for Andrew and Scott and then rearrange them in 2 factorial ways. Because 5p2 means that you, out of five, you choose any two and then you arrange them into then you arrange those two in 2 factorial ways, right? Yeah, so this is how you can do it. And again, the reason why we are able to multiply them is because of basic counting principle, just to emphasize, because of basic um, counting principle. Because what we're saying is that these four individuals can be seated in 4 factorial ways. And then what you can do is these four individuals can be seated in 4 factorial ways. And then for Andrea and Scott, you can choose five out of the five slots, five spaces between the five spaces that we have over here. You can choose any two and then arrange them in 2 factorial ways. So together you can do all of this as 4 factorial into 5 choose 2 into 2 factorial. So again, the reason, just to emphasize, we're multiplying them is because of the basic counting principle. And if we do it like this, the answer still turns out to be 480, similar to be found from method 1. So one method is that you find the total number of arrangements without restrictions, and from this subtract the arrangements in which Andrea and Scott sit next to each other to find the number of arrangements when they refuse to sit next to each other. The second method is we can seat these four individuals in four slots, and in between the spaces that we have, we can choose spaces for Andrea and Scott. But